Okay, so starting with compound interest, we have you deposit $2,500 in an account. That earns 8.7% annual interest. And that interest is compounded monthly. And I want to write and graph a function that represents the situation. So write and graph a function that represents this situation. First thing we need to do is write down the compound interest formula. So we learned the formula A equals P times 1 plus R over N to the NT power. So remember that P is principal, which is the amount invested or the amount that you start with, or the amount you deposit. R is the interest rate. N is the number of times it is compounded. And T is the amount of time that the money is invested, and T is measured in years. So now we're going to take the numbers from our problem and put them into this formula. A equals our principal, which is $2,500, times 1 plus our interest rate, 8.7%, so that's going to be 0.087, over the number of times it's compounded, and it says it is compounded monthly. So how many times is it compounded in a year? 12. Okay, and then that's to the 12 times. The time here is T. It did not give us a specific time. And remember, when we write a function, we still have variables in it. Like if I was writing the equation of a line, I would still have x and y in that. So I'm going to leave the T in there. Now I'm going to go ahead and simplify that a little bit. A equals 2,500 times 1 plus 0.087 over 12 to the 12t power. That's the function that I'm supposed to write. I'm also supposed to graph that. Now, to graph something with decimals that are this involved, you would have a calculator. So what I would do if I needed to graph this is graph it in my calculator and then go back and look at the table to help me get that graph onto paper. So graph it in the calculator and then go to table so you can see what it should look like. Okay, so that's what it looks like when we get it typed in. 2,500 times 1 plus 0.087 over 12 to the 12x power. Now, notice when I hit graph, I don't see anything. Don't panic when you hit graph and you don't see anything. What's the y-intercept of that function? 2,500. So we shouldn't expect to see anything because that's only going to go up to about 10. Our y-intercept is 2,500. It's way up there. So I should not be alarmed that nothing is on the screen right now. But I can still go to the table and see the values. So I'm going to press second table. Okay? And I can look at some of the values here in the table to help me transfer that graph onto some paper. Okay, next one. This table shows the value of a boat over time. We have year T, 0, 1, 2, and 3, and then we have the value Y, and it goes from $21,000 in year 0, which would mean when it's brand new, to $8,859.38 in year 3. The first thing we need to do is figure out if the table is going to represent exponential growth or exponential decay or neither one. It doesn't have to be either. Now, if it is exponential, it's going to show a multiplication pattern. The easiest thing to look at is whether it would be growth or decay. We're going from 21,000 to 15,750 to 11,812.50 to 8,859.38. Okay, so are those numbers going up or down? They're going down. So it is decreasing. It would be decay if it's going to be anything. We know for sure it is not exponential growth. It could still be neither. But it's definitely not growth. So now to figure out if it's exponential decay, I need to see if there's some sort of multiplication pattern going on. Now, what we typically do is kind of divide backward to see if that's happening. So if I go backward and divide, theoretically I should get the same thing each time. So take your calculator and do 8,859.38 divided by 11,812.5. And we get 0.75. Now do 11,812.50 divided by 15,750 and see if we get the same thing. We do. And just to double check, 15,750 divided by 21,000. And we do. So then, since we are observing that same pattern all the way through, we know that it is exponential decay. Part B, the car loses 25% of its value every year. Write a function that represents the value Y in dollars of the car after T years. Well, since it's exponential decay, we're going to have y equals a times 1 minus r to the t power. So y equals, what's the initial value? A is the initial value. What is that? 21,000. And then 1 minus r, which is the rate of decay. It loses 25% of its value. So 1 minus 0.25 to the t power. So that's y equals 21,000 times 0.75 to the t. Look, this was 0.75. If it's losing 25% of its value, then 100% minus 25% is 75%. And part C, use the function from part B to estimate the value of the car after 6 years. So we're using this function, we're plugging in 6 for t. So y equals 21,000 times 0.75 to the 6th power. We put in 6 for t. And you would use a calculator to evaluate that. So work that out. And you should get $3,737.55. You would have to bump that up because it's 0.548828, so it bumps up to 55. $3,737.55. Okay, next problem. Write an equation for the nth term of the geometric sequence using the formula a sub n equals a sub 1 times r to the n minus 1 power. Then find a sub 7. Okay, so I've got a sub 1 being 1 in this list of numbers right here. A sub 1 is 1. And then my formula, a sub n equals a sub 1 times r to the n minus 1 power. I have to find r. That's my rate of change. It's my multiplication pattern. So I go from 1 to 4, from 4 to 16, from 16 to 64, from 64 to 256. So what's my pattern here? Times 4. Okay, so 4 is r. And now I'm ready to write my function. A sub n equals 1 times 4 to the n minus 1 power. And I can simplify that if I want to and say a sub n equals 4 to the n minus 1. Okay, the next part of that is to figure out a sub 7. Well, I've got term number 1, 2, 3, 4, 5. So if I want to know a sub 7, I have to find 2 more terms. So I'm going to have to do 256 times 4. That's going to give me the 6th term, which is 1024. And then I'm going to have to do 1024 times 4, which is going to be 4096. So a sub 7 is equal to 4096. Now the next problem is another one where you evaluate for the given value of x. We just did one of those today in class. It simply means that we need to take the value of x that we are given and substitute it in and then work the problem out. We have y equals 2/5 times 5 to the x power. That's y equals 2/5 times 5 to the 3rd power because we have x equals 3. So y equals 2/5 times, now 5 to the third. 5 times 5 is 25, times 5 again is 125. So now I just need to know 2/5 times 125. Which is 50. So the value of the function when x equals 3 is 50. Number 10, write the rate of decay of the function as a percent. Write the rate of decay as a percent. Now remember, the rate of decay is r, and the decay function is y equals a times 1 minus r to the t. 25%, 0.25 here, is not the rate of decay. 1 minus r is 25%. 100% minus r is 25%. So in this case, the rate of decay is 75%. It's decaying by 75%. It is retaining 25% of its value, but it is decaying by 75%. An island's population decreased by 17% each year. In 1990, the population was 640,000. What was the population in 2000? Round your answer to the nearest thousand. Alright, so the population is decreasing. So this is exponential decay. So y equals a times 1 minus r to the t. It's a minus because it was decay. If the population was increasing, this would say 1 plus r, because it would be a growth function. So y equals, a is the initial value. That's where it starts out. That was 640,000. And then times 1 minus r is the rate of decay. It's decreasing by 17% per year, so that's 0.17. And then t is the amount of time. Well, it was 1990 until 2000. So in this case, t would be 10. So we have 640,000 times 1 minus 0.17 to the 10th power. So work that out. So this is all of the decimal places that my calculator showed me, 99,302.6636. But it says round your answer to the nearest thousand. Well, I've got ones, tens, hundreds, thousands. Okay, so I'm going to round off, and all I'm going to see after this second 9 right here is zeros. So the question is it 99,000, or is it enough to bump up and make it 100,000? And it is 99,000, because this number is a 3, so it's not enough to bump it up. So to the nearest thousand, we have 99,000. The next one is use your graphing calculator to solve the equation by calculating the x value of the intersection. This is like what we did in class today, so you need your calculator for this one. And the function that we're typing in is 4 to the negative x minus 1 power. 4 to the negative x minus 1 power. And then y2, the right side of that is 6 to the x plus 3 power. So 6 to the x plus 3 power. And we're going to graph. Okay, one of these was a growth function, the other was a decay function. And we're interested in the x value of this intersection. Now, in this particular one, it's pretty easy to tell just by looking at the graph that it's somewhere around -2, but we can't be 100% sure, so it's always best to do the intersection, to calculate the intersection. So second calc, and option 5 is intersect. So the first curve is the magenta one on my screen. The second curve is the red one. And then it wants me to guess. So I'm going to arrow to the left until I get to about where they intersect. And it says the intersection is -2.12753. On your test, I would tell you how I want that rounded. Let's go with the nearest hundredth. So I would say -2.13. So x equals -2.13. I have a table here, and I want to know whether it represents a linear function or an exponential function. First thing I want to do is see what is happening in terms of x. So from 0 to 1 plus 1, from 1 to 2 plus 1, and from 2 to 3 plus 1. And that's kind of what you look for. That's what almost always happens in problems out of textbooks and on worksheets. In real life, it's not always so nice, but most of the time when you have a problem, it's going to go in order like that. Then, I need to see what's happening with y. Y is really what's important here. Remember, if you have an addition pattern going on in y, we're probably looking at something linear. You want to check the slope to make sure that you have a constant rate of change, but an addition pattern implies linear, and if you have a multiplication pattern, that implies that it's going to be exponential. So the numbers on y are 0, 4, 8, 12. So what's our pattern? Plus 4. It is adding 4 each time. So I want to look at the rate of change in y over change in x, and each time it is 4 over 1. So my rate of change is constant at 4, and since it has a constant rate of change, then I would say that this table represents a linear function. Okay, here's another table. Again, on my x's, I'm counting by ones. On my y's, I have 5, 25, 125, 625. So what kind of pattern is happening for y? Times 5. Since I have a multiplication pattern, I would say that my pattern is exponential. My rate of change is multiplying by 5. I have a constant ratio, and if I needed to know the constant ratio, then it would be 5. All right, I have a function here, f of x, or f of t, equals 36 times 1.07 to the t power. And I need to identify the initial amount, a, and the rate of growth, r, as a percent. And then I also need to evaluate it when t is equal to 7 and round my answer to the nearest tenth. So a, the initial value, is this number out front. So the initial value is 36. R is the rate of growth. Remember, inside the parentheses, it's 1 plus R. This is 1.07. That means R is 0.07. And it says to give it as a percent. So R is 7%. And then evaluate the function when t is equal to 7. So I would write f of 7, don't forget to sub your 7 in right here, equals 36 times 1.07 to the 7th power. And that's when I would use a calculator. So 36 times 1.07 to the 7th power. That is 57.8, rounded to the nearest tenth. Okay, next section. Determine whether the graph represents an exponential growth function, an exponential decay function, or neither. Remember, you always read a graph from left to right. So as you move from left to right on this graph, is it increasing or decreasing? Decreasing. It's going down, so that makes this exponential decay. Okay, and the next one, as I go from left to right, it is increasing. So this one is exponential growth. And this last one is something you haven't learned yet. It's just kind of wiggly. It's actually a sine function, S-I-N-E, and you'll learn about it next year in geometry, and you'll do a lot more with it in trigonometry. So this one is neither. It is not exponential growth or exponential decay. It is a sine wave. You would not have to know that it's a sine wave. You just need to know that it's neither. I like this next problem. It kind of makes you think and go through a few more steps. It's not straightforward. At noon on Tuesday, a kiddie pool is filled with 54 gallons of water. The pool has a leak, causing it to lose 1.8% of its water each day. When the pool reaches 51 gallons, more water will be added. On what day of the week will more water be added? Use the trace feature of a graphing calculator to help find the answer. Well, before we can use the calculator, we have to know what it is we're graphing. So we have to come up with the function. Now, we know it's exponential decay because it has a leak. It is losing water. Okay, so exponential decay, y equals a times 1 minus r to the t power. A is the initial amount. We start out with 54 gallons. So y equals 54 times 1 minus, it is losing 1.8% per day. So 0.8%. 0.018, and we're supposed to figure out the amount of time that's going to pass before we need to add more water. So in other words, we're looking for when does Y drop down to 51 gallons. We want to know when Y is steadily decreasing, when it's going to get to 51 gallons. So at this point, we're ready to use the calculator. We're going to type in Y equals 54 times 1 minus 0.018 to the x power. Okay, so I'm going to get my calculator. And I need to look at the table. So I'm going to press second table. Well, there we go. So I see my starting value here, 0.54. And you can see these numbers are getting smaller each day. So on day 2, there are 52.073 gallons. On day 3, there are 51.136 gallons. And on day 4, there are 50.216 gallons. Somewhere in between day 3 and day 4 is when it's going to get below 51 gallons. Okay, now the problem said when it reaches 51 gallons. So it's going to happen before day 4 occurs. It's going to be after 3 days, like at the end of 3 days, but it's before we get to the end of 4 days. So it says at noon on Tuesday. So what day is it 3 days later? Friday. 3 days later, it will be Friday. So that means that on Friday, we will have to add more water. And I'm sorry, that said trace, not table. I used the table. You can also use the trace function like it said to. Once you get the graph on the screen, this is the graph. Now press the trace button and it pops up your X and Y values right here, and you can trace along that function moving left and right until you get to a point where the Y value changes to 51. And if you trace that, you'll see it's going to change to 51. Oh, it took off. Changes 51 between days 3 and 4, like we said before. So it's going to happen on Friday. All right, graph the function f of x equals -2 to the x power on your calculator. Then graph g of x equals -2 to the x power plus 6 on your calculator. Describe the domain and range of each function. Find the y-intercept of the graph of each function. How are the y-intercept, domain, and range affected by the translation? Okay, so I'm going to graph that first one. And the first one was y equals negative 2 to the x power. The second one was y equals negative 2 to the x power, and then arrow out of your exponent and say plus 6. The first graph is this magenta one. The second graph is the red one. Describe the domain and range. So for f of x, the domain, this is all the numbers that can be plugged in for x. What's x allowed to equal? Anything. So the domain's all real numbers. The range is what y is allowed to equal. Now remember, the first one we graphed, f of x, is the magenta one. So what are the y values? Less than 0. So y is less than 0. For g of x, the domain is, again, all real numbers. You can plug in anything you want to for x. And the range, the y values. What are the y values for the red one? Y is less than 6. 1, 2, 3, 4, 5, 6. Y is less than 6 is our range on that one. Part B of that wants to know the y-intercept. The y-intercept for f of x, that is where it crosses the y-axis, is negative 1. And for g, the y-intercept is 1, 2, 3, 4, 5. And part C of this problem, how are the y-intercept, domain, and range affected by the translation? Well, you can see that the y-intercept has gone from negative 1 to 5. So the y-intercept has gone up 6. Okay, and that should not be a surprise to us because we graphed y equals negative 2 to the x plus 6. That plus 6 is what caused the y-intercept and every point on the function to move up 6 units. It does not affect the domain because the domain is all real numbers for both of them. So you can still plug in anything you want no matter what. The range, though, was changed. The range was y is less than 0, and it became y is less than 6. The range changed by being translated up 6. Since all of the values were translated up 6, the range was as well. So the y values now can go all the way up to 6 instead of just to 0. Okay? So those are all the review problems that I have. I'm going to go ahead and shut the video off at this point because it's already pretty long. Make sure you study. Make sure you have your calculator tomorrow. Make sure it's charged up so that you will be able to use it on your test. You will absolutely have to have your graphing calculator on the test.